Okay, the first example we're going to look at, this example is not on the textbook. It's an example of a box. And we have this is a smooth surface, so no friction. And if we apply a force at the bottom of the box, dragging this box, sliding along the surface, that's F. And we want to know what's the maximum acceleration you can apply to this block without cause tipping. Tipping means this block will rotate either rotates to this side or on the other side. So what are the givens here is we know the width of this block, which is W. Also know the height, H. So now you can see why this is a rigid body kinetics. In the problem statement, they will give you the dimension of the rigid body, which in other words, tells you the dimension, the location matters. So when you draw your free body diagram, where you put forces on the rigid free body diagram could have a big impact on your result. So let's write out all the given information. We know W, we know H, we know mass. What we don't know is what's the maximum acceleration without causing tipping. So that's what we try to find. Okay, let's use the 6-step approach we'll learn last Wednesday. Step 1 and 2. Free body diagram. This is our box. For free body diagram, we have the force F. See, I don't change the position where the F is applied, because the position the force is applied matters in this chapter. And how would you draw the weight force? The weight force can be going downwards, but where you apply that matters. So usually weight force will pass through this mass center. That's called the mass center G. Weight force gonna be this. And what other forces we have here? Is this, do we already have all the forces on free body diagram? Who can tell me what's the other force we need?
Normal force?
Yeah, we need to have a normal force. But where do we apply that normal force? If this block is just sitting on the table and without moving, the normal force will just pass through this center mass pointing upward. But since here we're looking at this extreme condition when before this box is tipping, so the normal force in that condition would be at the edge of the box. So this is how I would draw my normal force. Right before tapering, that would be at the edge, pointing upwards. And second step, we need to set up coordinate system. Of course, in this problem, INJ would be enough. Okay, so now we finish first 2 steps. Not too bad. Let's look at step 3 and 4. Step 3 is write all the forces in vector form. We have F in vector form. It's gonna be Fi. Normal force gonna be Nj. Weight force gonna be -mgj. Step 4, acceleration. Here, pay attention, extra attention. In this chapter, all the acceleration of rigid body should be the acceleration of the mass center. So I add AG there to tell myself this is the acceleration of the mass center. This is AG. Since the box is only moving on I direction, so acceleration is only on I direction. Okay, step 5. Now it's the time to apply Newton's second law. Sum of all the forces goes ma. And this is a vector equation. We can break that down to I and j. On I direction, all the forces we have is the F force. That's it, equal to m a g. On j direction, we have more forces, which is normal force minus mg. That gives us, since we don't have acceleration on j direction, therefore 0. And so far we have 1 and 2. We have 2 equations. And another equation we can create, which is based on the Wheeler's second law. Sum of moment. But pay extra attention here. Whenever you're talking about sum of moment, remember moment, it's a vector, and you first define what is a positive direction for moment. Moment is rotation. So here we define if the rotation is counterclockwise, that is positive. And also moment can only be written in terms of a point. So you need to tell the equation which point you're talking about. So that's related to the 3 special cases we mentioned. And we always want to find a special case that can simplify the equation. I will write the general equation, which is I alpha plus, if I remember correctly, that would be R G slash A cos M A G. Oops, M A. So that's a full equation, right? And if you can find any special cases, then you can get rid of the second term to make this easier. So now we want to look at our problem to say, do we have any special point we can choose to simplify our equation? In this problem, yeah, we do have center mass. So that's a special case 1. We can pick that point to simplify our equation. And we don't really have special case 2 and 3. So let's just follow case 1, which is pick mg, moment about g. Then we can get rid of the second term. And make sure you add notation for your I. In this case, since you pick g, your I becomes ig as well. Okay, now let's first look at what are the sum of moments from each force. Go back to free body diagram. Look at this first force, normal force. What's the moment caused by this normal force about G? First, look at what rotation, direction of rotation we have. And it's here, G is here. The rotation caused by N would be clockwise, if you can see that point G. So that moment is negative. The distance between N and the G, it's half of the width. In this case, width is given as W. So we can write the first moment caused by normal force, which is negative N, times the distance between normal force and the point G, which is half of W. Okay, that's the first moment. Let's look at the second force, which is wave force. This wave force passed through that point G. That means the wave force will not cause any rotation or movement about point G. So any force that will pass through the point we're talking about movement, not cause movement. If that makes sense. Okay, so 0 here. If you look at this force does cause a movement about point G. And the distance between F and G is half h, and the rotation gonna be counterclockwise, so it's positive. So let's write the second one, positive F times h over 2. And sum of those two moments equal to Ig alpha. Now we have the third equation. Here, just want to make it clear, since here, first equation is on I direction, second equation is on J direction. The third equation we have here, it's on K directions. It's all the movement or rotations in terms of K direction. Okay. Now, if you look at the equations, we know what is the mass, and we don't know Ag. That's something we try to solve. From this equation, we know N equals mg. From the third equation, Ig, I think that can be found from the table. Force, F, we don't know. And we do know H and W. And we don't know what is alpha. What is alpha? What does alpha mean in chapter 2, rigid body kinematics? Alpha is acceleration. What acceleration? It's angular acceleration of the rigid body. So if we go back here, we want to find out the case that without any tipping, another word is without tipping. So without having the rigid body rotate like this, right? This is kind of like rotation of the rigid body. So alpha tells us how fast that rotation would occur. Since here we're looking at without tipping, that means we don't want to have any alpha angular acceleration, if that makes sense. So that's kind of the hidden information in this problem. So that alpha in this problem is 0. Okay, so let's just look at equation 3. If alpha is 0, right hand side is 0, then we end up with NW2 plus FH over 2 equal to 0. And we can find what is F, since we don't know what is F. F gonna equal to mg W over H. So we get expression for F. Since here we are trying to find what's the relationship, what's the acceleration. However, here we find this is the maximum force you can apply without causing tipping. So similarly, the maximum acceleration is going to be just F mx over by mass, which is g W over H. That's how you solve this problem, find the maximum acceleration without causing tipping. If this is making sense to you. All right. That's about this example. Any questions? There's some similarities between this 5A and chapter 4A. Also, there's a significant difference between these two chapters, sections. Difference start from Euler's second law. Let me highlight this. You need to pick a point that could simplify the equation before you solving unknowns. All right. Now let's look at one more example. Okay, in this example, we have a slope. And on a slope, we have two rigid body. One is in the shape of a ring, and another one is in the shape of a disc. So we have a slope is the angle theta. On the top of the slope, we have a ring. It's just different color. That's a ring, and on that also we have a disc. Okay, if they're both released at the same height on the slope, and which one will reach the bottom first? Would you say it's the ring or it's the disc? Yeah, of course, I should tell you some information about this ring and disc. So we know they have the same mass, same radius, r, and we do have friction on the surface. So they're both rolling without slipping. If that makes sense. Okay, now I want you to kind of vote which one will reach the bottom first. Write down your answer on the chat, Zoom chat area. Do you think should be the ring or the disc? Or you think they will reach the bottom at the same time? Or maybe they will never reach the bottom? Okay, the majority of you think it's a disc. Some of you think it's a ring. We have all the answers. I think I've someone did this example online and they made a video of it, so we can take a look to see what's the result looks like. Okay, so I think you probably can see this video, and they have here they have three objects, a kind of ring, disc, and a ball, a solid ball. Here, ring, the cylinder means it's a disc. The same case for our disc. Wow, the result is pretty obvious. The disc reached the bottom first, then the ring. So congratulations to the most of the class, you got it right. But why? Yeah, the video someone did experiment proves that why disc reach the bottom faster than a ring? And we can use dynamics to prove why. Right? You can just use the 6-step approach we did in the previous example to solve this problem. So let's look at step 1, 2. Draw a free body diagram for both ring and disk. Ring and disk. Sorry about my skills drawing circles. Pretty hard to do. Okay. Let's first look at wave force, right? W and W. Since they both have the same mass, so the wave force is the same on free body diagram. What other forces we may have? Since we do have friction, so we should have friction force that is acting along the surface, FF. Same friction force here. And besides friction force and the wave force, this is on the slope, it should have a normal force perpendicular to the surface. Okay, now we finished free body diagram for both ring and disk. Something interesting you may find out. Doesn't matter about your shape, as long as you have the same radius and same weight, both ring and disk end up with the same free body diagram, if you can see that. Wave force, normal force, and friction force. And the second step is set up coordinate system. And we can definitely set up coordinate system like vertical J, I. We can also rotate our coordinate system to line up with the slope of this problem, which is J, I. In this example, I would pick the coordinate system with angle to kind of simplify my solution. Okay, now we have first 2 steps done. Third step, write down all the forces in vector form. That shouldn't be too
Dr.
hard.
L.
Yep.
You're not sharing your screen. We can't see your work.
I'm sorry. You should tell me earlier. Oops. Totally forgot that. I'm sorry. Now there you go. Free body diagram for ring and disk should have 3 forces on the free body diagram: wave force, normal force, and friction force. The friction force and normal force are perpendicular to each other. And the friction force has the same angle as theta. And how we set up our I and J coordinate system would line up with the slope. And the third step gonna be write down your forces in vector form. So N can be Ni, F gonna be negative. Oops, I think I did a mistake here. The normal force is on J direction. For friction force, it's on the negative I direction. For the weight force, due to how we set up the coordinate system, our wave force is going to have both I and J components. And you need to use information on theta to find the components. So on I components, we have mg times sine theta. On J direction, we have negative mg cosine theta. That's J, that's I. Those are all the forces. For acceleration, see that? You should always write acceleration of center mass as AG. Since this both ring and disk can only move along the slope, so the acceleration is on I direction only. Step 5, apply Newton's second law. Sum of all the forces, and to break it down to I and J, find two scalar equations. You end up with I direction, we would have negative F plus mg sine theta, and the acceleration on I direction going to be mag. For J direction, only have this normal force and the J component of weight force, which is mg cosine theta. The acceleration on this direction is 0. We don't have J components for A. Therefore, here is 0. Now we have first two equations from Newton's second law. Okay. Can you guys see my screen? Just wondering.
Yeah.
Okay.
Yep.
All right. So something new we learned last Wednesday is once you have the Newton's second law, we're going to apply Euler's second law to sum of all the moments. Like I said, mentioned in the first example, you first need to define the positive direction of the movement, which is counterclockwise. Then you need to pick the point that can simplify your calculation. And let's look at this free body diagram here. What are the special points we can pick? Let's call the center mass as G. You can call this contact point C. We can go through all the three special cases. Special case 1 is when you pick the point that is a center mass. We do have that. So if you pick G, that would be your case 1. If you pick C, which case gonna be? C is the contact points, the disk and the slope. If I give you more hint, this is no slip condition. If we pick point C for our Euler's second law, which special case we're talking about? Is that case? We already did case 1, so that won't be case 1. Is that case 2 or case 3? If we pick point C. If you look at case 2, it's when you have a fixed point on your rigid body. So the whole rigid body is rotating about that fixed point. And if you look at both ring and disk, we don't really have a fixed point, right? So that's definitely not case 2. If you look at case 3, you should have a point Q on the rigid body that is parallel to the position vector RG/Q. And that's we mentioned that's a similar case as no slip condition. So if you pick point 3, you are actually using case 3. If that makes sense. Okay, so you can have two different approach for this problem. Either use pick G for case 1, or you can pick C for case 3. So let's pick point C. So pick point C, find moment about point C. And this will simplify our equation to just IC times alpha. Okay, now let's find out all the moment about point C from that free body diagram. this is our point C. If a force passed through the point C, it would not cause movement above point C. Does that make sense to you? So always keep that in mind. Since both friction force and normal force pass through point C, they both would not contribute to the movement above point C. And another force we have here is weight force. The weight force would contribute to the movement above point C. And since we're using an angled coordinate system, let's break down this weight force. The weight force has this I components and J components. If you look at the J components, this WG. WG will pass through point C, which means it would not cause any movement about point C. So the only force will cause movement about point C here is this WI, the weight force on I component. So I would write down the weight force on I component, which is G cosine theta. Oh, sorry, that's on J component. On I component, that should be sine theta. Times the distance from the force to the point. Since the WG passed through the center mass, the distance between center mass and point C, it's just the radius R. So that's R. Oh, we're not done yet. This is just force times distance. You need to judge what's the sign for this moment. As we defined, positive direction is counterclockwise. If you look at this force, it will cause a clockwise rotation about point C. Therefore, the moment is negative. So let's add a negative sign here. And that's all the movement we would have for sum of moments about point C. This will equal to IC alpha. If that makes sense to you. Here, I don't need that vector notation. And first equation, we have on I direction. Second equation, we have this on J direction. This third equation, it's on K direction because this is movement. It's about rotation. It's on K direction. If we look at just third equation here, we can find the expression for alpha. Alpha equals to mg sine theta times r divided by IC. Why this equation would be helpful? Let's go back to the problem. What we try to find is which one would reach the bottom first. That's a problem of acceleration, which means which one would have the large angular acceleration to make sure it's rolling faster and reach the bottom faster. So that's about which one has the large alpha. Now we have expression for alpha. Instead of alpha on the top, we have negative mg sine r. We know they both have this mass m, and this theta is fixed. The radius are the same. So on the top, we don't really get any information for alpha. But if we look at the bottom, that's IC. That's a moment inertia at points of about point C. And last time we learned the parallel axis theorem. So you can find moment of inertia of any point by using this formula. IC equal to IG plus m times d. D is distance between C and G. Square. So we can replace this IC with this formula. This dCg here is just the distance r, the radius r, if you can see that. So let's rewrite this alpha equal to Ig plus m r squared. On top we have negative mg sine theta r. Okay. Now if you look at this new expression for alpha, there's something different about the ring and the disk is this Ig. Ig, it's the moment inertia. For different geometry and shape, you're gonna have different moment inertia. So for disk, for ring, the moment inertia Ig of a disk is mr squared over 2. For ring, it's just mr squared. Okay, now the answer is pretty obvious. Disk, if we they share the same mass and radius, a disk will have smaller moment inertia, and ring gonna have large moment inertia, and that reflects on the angular acceleration would be the disk, since it has a smaller moment inertia, so smaller, you get a smaller value on the bottom here, and you would give you a large angular acceleration alpha. Therefore, a disk will reach the bottom faster than the ring. So let's try that. Our disk gonna be large than alpha ring. Okay, so that confirms with the experimental result you just watched on that video. Yeah, if any questions, do you think everything makes sense?